Hello, good evening. Welcome you all to the live session 10 on the course Fundamentals of Manufacturing Processes. In this session, we will try to solve some sample problems based on the video lectures of week 10. So, let's get started with the first problem. Please read the problem and try to find out the correct answer. After that, we will discuss it together. Okay, hopefully you have tried and you have got the answer. Okay, uh, let's start discussing it together. So in this question, what has been asked: high depth of cut and low feed rate are used during, and these are the uh, names of the different grinding processes, so like cylindrical grinding, creep grinding, surface grinding, centerless grinding. So we will try to see one by one uh, in which we will get the high depth of cut and low feed rate. So let's get started looking each options. First one is the cylindrical grinding. Hello, sir. If you want try this problem, please take some time and you can try it. You can answer it in the chat box. Yes, correct. Creep grinding is the correct answer. Okay, now let's continue our discussion. Let's start looking each grinding process one by one. So first one is the cylindrical grinding. So this is the schematic of the cylindrical grinding. This process is used to grind any cylindrical object, or this process is mainly used for to surface finish. It may be internal surface or it may be external surface. So here our workpiece is cylindrical in shape. Like here, this is the example of the external grinding. This one is the external. Basically here we are trying to improve the surface finish of the external surface of the workpiece. Similarly, we have internal grinding also, internal cylindrical grinding. Here this is the grinding wheel, and here this is the grinding wheel. And we are trying to improve the surface finish of this workpiece internal surface. So this is the internal surface, and with the help of the grinding wheel we are trying to improve the surface finish, internal surface of this cylindrical workpiece. So this is the cylindrical grinding. Let's move to the creep grinding. This is example of the creep grinding. Basically here we want to manufacture some profile on the workpiece. Like here, this is not an very easy shape, and this this creep grinding basically mainly focuses on the MRR, whereas the in earlier grinding process like cylindrical grinding, that was a kind of surface finishing process. But here we are just trying to make this kind of profile. What is there on the grinding wheel, we want to make the similar kind of profile on the workpiece, and we are doing it in one go. So that's why we have to give high depth of cut, and since we are giving very high depth of cut, therefore we cannot go for very high feed rate, because grinding is a very heat intensive process. Lots of feed get produced. So if we are providing high depth of cut, so we have to give very small feed rate, and we are creating this profile just by in one go. So this is the creep grinding. Here we want to manufacture the profile in one go, and it is mainly used for the sometimes if geometry is a little complex, or we have a workpiece material which is not easy to machine with other methods like milling. So in that case we go for the creep grinding. So let's come to the next grinding process, that is the surface grinding. Here we have a surface. This is the workpiece, and we want to improve the surface finish of the top surface of the workpiece. And here we have grinding wheel, and with the help of this grinding wheel we are just trying to improve the surface finish of the top surface of the workpiece. Similarly, there is another configuration. Here we have grinding wheel like this, and there are many. These are the surfaces which we are trying to improve its surface finish. So here we are improving the surface finish of the top surface of the workpiece. So that is called the surface grinding. And let's move to the next process, which is centerless grinding. It is also a process which is used to improve the surface finish of the cylindrical object like shaft. So here what is done, here our workpiece is kept in between two grinding wheels. This one is the grinding wheel, and another one is the regulating wheel. So there are the two different views. This is the side view, and this one is the top view. So here this is the grinding wheel, and our workpiece is kept in between these two grinding wheel and regulating wheel, and there is a rest blade over which our workpiece is kept, and there is some inclination angle given to the regulating wheel. And because of this inclination angle, like here, because of this inclination angle, our workpiece gets feeded in between the wheel. Here we don't have to provide extra feeding mechanism in order to grind the whole surface of the workpiece. Because of rotational speed of this regulating wheel, our workpiece will get automatically feeded in between the grinding wheel and regulating wheel, and whole surface get and come throughout the surface. The grinding happens, and the feed motion is just is provided by this because of this inclination of the regulating wheel. So that is the centerless grinding. So one thing we can see in the cylindrical grinding, surface grinding and centerless grinding. Our aim is to improve the surface finish of the workpiece. Whereas in the creep grinding, we are trying to make a complete profile with the help of uh, grinding. So therefore, we have to give high depth of cut in order to make that kind of deep profiles. And since we are giving high depth of cut and lots of it is being generated, so we have to reduce the feed rate. So the correct option for this question will be creep grinding. And just for the comparison purpose, we can see to what extent the properties differs between creep grinding and other grinding, where our aim is to improve the surface finish. Here we are taking example of reciprocating grinding. Basically it is a surface grinding and creep grinding, and we can see here depth of cut is very high, whereas here depth of cut is very minimal. Here our aim is to just improve the surface finish, whereas our aim is to remove the lot as much of material we can. Here we need high MRR. Here we don't need MRR, we just need to improve the surface finish. Therefore we can see depth of cut here we have 0.001 mm to 0.1 mm, whereas here depth of cut is very high. It goes from 1 to 12 mm, which is too much. Similarly, speed, workpiece speed in meter per minute, here we have 10 to 40 meter per minute, but here we have lesser workpiece speed. So similarly we can compare other properties like wheel speed. Wheel speed is almost, there is not much difference in the wheel speed, but there is a significant difference in the workpiece speed, that is also feed. So here we can see we can give higher feed, but here the feed value is very small, but depth of cut is very high. Similarly other differences we can see, like arc of contact, like here very small arc of contact is there. If we try to show the arc of contact, here it's very small, whereas if we see arc of contact, it is larger here. So we can see in the case of creep grinding we have arc of contact much higher than the case of the surface grinding. And MRR also, here we have very small MRR, but here we are getting very high MRR. And in the grinding process we try to improve the surface finish by giving a small depth of cut but many passes. Sometimes we have to go for 10 passes or more than 10 passes, but here we are getting the final component just in one pass, because we are giving high depth of cut one time. So I think I have explained the problem number 1. Still, if any doubts, if any one of you have any doubt, please let me know, otherwise I will move to the next problem. It seems there is no doubt. Let's quickly move to the next problem. Please read the question and try to solve it by first by yourself, then we will discuss it together. Meanwhile I will create the polls. You can give your response in the polling section. polls are live, please try to solve it by yourself first, and you can give your response in the polling section. And if you are facing any difficulty to understand the problem, please let me know. Yeah, I am waiting for a response. Yes, I have got a response. Okay. Okay. Uh, let's try to solve it together, and later on you can see you can match your solution with it. So let's first try to understand the what has been asked in the problem. So question is like this: in central standing, we know in central standing we have workpiece which is grinded between two wheels. One is the grinding wheel, another one is the regulating wheel. So here the diameter of regulating wheel is 150 mm, and it's rotating at 3000 rpm, and there is a inclination. We know there is a inclination given to the regulating wheel, and because of this inclination we get feed motion in the workpiece. So that inclination angle is 5 degrees. And what we have to find, we have to find out feed in meter per minute. So let's quickly try to draw the diagram. So I am making the top view here. Here we have a grinding wheel, and on which and here we have our workpiece. So our aim is to grind the surface of this cylindrical workpiece. So first we have grinding wheel over which we have the workpiece, and there is a regulating wheel which is at inclination of 5 degree from the vertical plane. So it will look like something like this. So this angle, this is 5 degrees. So we have grinding wheel that is black in color, grinding wheel, black one is the grinding wheel, this is the workpiece, and this one is the regulating wheel. And the inclination angle which is given to the regulating wheel is 5 degrees, and because of this 5-degree inclination, when our regulating wheel rotates, then it will basically if we'll try to see, so if we see just this point where the our regulating wheel is getting where our regulating wheel is coming in the contact of the workpiece, what will be happening there? Our regulating wheel is having some RPM like this, it is rotating. So because of this angle at the point of contact of the regulating wheel and the workpiece, there is we will the net velocity, net tangential velocity which we will be giving, which will look something like this, and it will be inclined to the, so let's call it that velocity is v, and that is inclined with the vertical axis by 5 degrees. So there will be two component of this velocity v. So I should, since our wheel rotation is, I am assuming in the clockwise direction, so for which direction will look like something like this at the point of contact, it will be 5 degrees. And if we try to decompose this velocity into two parts, so it will be like this. So because of this component, our workpiece will pulled pulled towards the left, and therefore our whole workpiece get feeded in between the regulating wheel and grinding wheel. So this component will be the, suppose if it is v, then this component will be the sine component of this degree. So that will be, so if we know this velocity v, then what we do, we will multiply this velocity v by sine of this angle, then we will get the feed component. So v sine this 5 degree, it will be the this equation, basically this value will give the feed rate or the feed speed. So now let's start putting the values. Here we are calling I to the inclination given to the wheel, and wheel diameter is basically, this is the dr is the diameter of regulating wheel. Regulating wheel, and nr is the rpm of regulating wheel. And the values which we are given, dr is equal to 150 mm. Let's convert it into the meter, because answer which we have to give, it will be in the meter per minute. So we will convert this diameter of the wheel into the meters. It will be same as 150 divided by 1000 or 0.150 meters. And RPM, rotational speed, is given 3000 RPM. And now we have to find out the feed in meter per minute. So I told that in order to find out the feed, first we have to find out this velocity v, and this velocity is given by pi into basically 2 pi into radius of the wheel into omega, and this omega should be in radian per minute. This omega will be in rpm only, because in order to find out the radian we are multiplying it by 2 pi. So 2 pi omega will be in rpm, and if we divide it by 60, then what we will get? We will get the angular velocity of the wheel in radian per seconds. And if we multiply this whole quantity by this r, so we will get this velocity v. Now we will try to put the values in this formula. So we will get 3.14 multiplied by 2, and here r is the radius of this regulating wheel. Basically that will be the half of the diameter of the regulating wheel. That will, if we directly put into the meter, it will be 0.150 divided by 2, and the rpm value which we have, that is 3000. So it will go away. So now what we will do, now we got the v value this much, but we have to find out the feed. So in order to calculate the feed, what we have to do, v multiplied by sine of 5 degree. So again what we will get, 3.14 multiplied by 0.150 multiplied by 3000 multiplied by sine of 5 degrees, and if we solve it, what we will get, 123.213. So this is the feed speed in the meter per minute. So the correct answer for this problem is the first one. So if any of you have doubt, please let me know. If anywhere you find difficult to follow me, please let me know. If it's clear, then we can move to the next problem. Okay, it seems there is no doubt, but later on, if you find any difficulty, please let me know. Okay, let's move to the next problem, but before that, here, since we have been asked the feed in meter per minute, so we don't need to divide it by 60. So here 60 is not required. If it is if it was asked like we have to find out the meter in per second, then we should have divided it by 60. Okay, let's move to the next problem. Okay. Yes. Please read the problem and try to find the correct match, and you can give your response in the polling section. Meanwhile, I will create the poll. After that, we will discuss it together. I have launched the polls. If you have got the answer, you can give your response in the polling section. After that, we will discuss it together. Yes, I have got a response. I'm waiting for others. Okay, I I have got the response from both of you. So let's quickly discuss it together. So we know in the joining process, especially in the welding, there are many configurations uh, in which we try to join two objects together. So let's look at let's try to look at different joint configuration in which we go for the welding process. So here we can see it's a cross-sectional view of the all joints. So here we can see we have a butt joint where uh, two components are brought together, and in between, end to end, we are trying to join them by melting them and filling by adding some filler material in between them, like here. And similarly, we have case of the lap joint. So we try to join the two bodies by there is there is a some common area and over which they are kept, and we are trying to join them by adding the filler material to the these two corners. And similarly, we have corner joint, and we have edge joint, we have T joint. So let's try to match, try to find the correct match. So here in this case, let's try to find out the first one, lap joint. In the lap joint, we know there is some common area between two joining bodies, and they are uh, and and they are joined by applying the welding materials to the both of the contact edges. So if you see this one here, they will be joined like this. Similarly, uh, if you see back side, there will be another set of joint, another set of welding material deposited between these two plates. So if we try to cut this, and if we try to see the cross sectional view, it will look like something like this, similar to the lap joint. So this one is the correct match for the lap joint. And similarly, in the we try to see the which is the butt joint. Butt joint, their two components are joined end to end, and we can see here we have both components, and we are trying to join them by adding some filler material in between these two uh, fang surfaces. So if we take the cross sectional view, it will look something like this. So that is the butt joint. And now similarly, if you try to see the configuration which is similar to the corner joint, it is here. So welding material will be deposited here, as well as the inner part also, like here. And if we take the cross sectional view, it will be similar to like this. And now we have edge joint, it will be looking like this. So what we do, we deposit the welding material on this top face, where we have the boundary of where we have the edge, where the edge of two fang surfaces are getting coincide, and we are depositing material over it. So if we take the cross sectional view, then again it will look like this. So that is the edge joint. And now let's try to find out which is the correct match. A2, B1, C3 and D4. Okay, the correct one is the second one. Okay, yes, I have explained this problem. So still, if any of you have doubt, please let me know. Otherwise we shall move to the next problem. Okay, it looks like it's clear to everyone. So let's move to the next problem. Please read the problem and try to find out the correct answer. Meanwhile, I will create the poll. You can give your response in the polling section. Yes, polls are live. I have got one response. I am waiting for others. Okay, I have got the response for both of you. Okay, let's try to look at the problem together. So it is given in T joint configuration, high stress concentration formed at. So First of all, let's try to recall what is the stress concentration. So if you can remember, uh, we have studied in the solid mechanics that because of the geometry uh, of our component, and when we try to apply some force on a component, and because of geometry there are certain points where there is a concentration of stress happens, and components gets filled at particularly at those points. Suppose if I will take an example, uh, I have let's say we have a component which is looks like this, and we are applying some load over here, F and F. So if component geometry is like this, then throughout the cross section everywhere we will get the same stress value. But suppose if we have a component something like this, where we have a hole, and again we are trying to apply the same force, what will happen? So there are near the hole we will get the, we will get our cross sectional area something like this. So here all the force is getting transferred to the very smaller areas, therefore here just at the top point and bottom point of the this hole, we will these will be there, we will get higher stress values compared to, let's say, here the stress value is given by F by this whole area, but here the stress value which we will get, nominal stress values, it will be given by another area, we are calling it A. So this plus this, and since this area is smaller, so stress value will be higher here, and the probability of failing component will be higher at these points. So these are the points of the stress concentrations, and this happens because of the geometry of the body. Now let's try to look what happens in the case of T joint. Normally we have T joint which look like something like this. This is the one component and this is the another component, and we are joining it by welding. So weld material is deposited at the corners like this. If you look at it in the 3D, it will look like something like this. So this whole regions weld will be deposited. Likewise other side also. So now let us try to look here. Okay, what I will do, I will remove these things. Okay, so here here we have T joint. Here we have a component here, and it is kept it is now it is joined with another component in the T configuration, and filled material is deposited here and here. Suppose if this whole material was not there, just this beam was alone, so then it will look like something like this. But here when we brought another another component and we have jointed them like this, so when this beam was alone, and we had applied some stress, some vertical force V, and we applied some horizontal force H, and because of these forces some stress will generate to the cross section of the beam. So if this welding thing will not be there, then the stress value which we are getting, like if we see this cross section here, the stresses are distributed something like this. Here it will be higher, then it will keep on reducing. And if we see in both cases, one where our beam is alone in the cantilever configuration, and second one is we have our cantilever beam along with another component joined in the T configuration. So if we see, this is the cross section near the welding portion. So if you recall, then these regions, the corner regions, these are called the toe of the welded joints in the T configuration, toe of the joints. Similarly, we have another toe here to here, and we are applying some horizontal force, some vertical force in both cases, and we are looking the distribution of stress throughout the beam. So if we see a cross section which is very far away from this toe, like here it is far away from the toe, here for the same loading conditions we are getting the similar kind of distribution of nominal stresses, which is similar, almost similar in the both cases, here and here similar. Now if we try to look the stress values near the toe, here near the toe, if we take cross section of the beam, and at the same location if we take the cross section of the beam where there is no welding is there, where only beam is there. Here if there is no welding in the T configuration, the stress distribution will look something like this. But again, here when we joined the two components by the welding, and we are looking near the toe of the weld, the stress distribution will be looking something like this. What is the difference here? Here we are getting this sigma nominal value. Here also we are getting the same sigma nominal value, but if we see the peak of this peak near the welded joint, it is much higher than the sigma nominal value, and this happens because of the change in geometry. This happens because of abrupt change in cross sectional area near the toe of the welded joint, and because of this stress concentration, here the sigma peak is much higher than sigma nominal, and this peak value comes because of the T joint, because of geometry change due to joining process, and that is this region is called toe. So abrupt change happens near the abrupt change of cross section happens near the toe, therefore we are getting higher stress value, and this point is called the stress concentration point. So if we keep on applying the load, then component will fail. It is most probable to fail near these 2 points, here and here. So correct answer for this problem is the toe of the weld. Whereas if we see other options like top plate, we are applying the force on the our this vertical beam. So in top plate also, if we will see, these are the points where we will get some stress value, whereas the other points we will not get any stress value. So top plate, we will, the component will not fail, the top plate will not fail if we apply the load on this horizontal plate. Similarly, in the bottom plate, it is the bottom plate, but bottom plate will fail near the toe. It's not like anywhere it will fail in between. So near the toe, it has highest chance of failure, and that will happen because of stress concentration, and that is happens because of the change in abrupt change in cross sectional area near the toe. And joint interface, if you see, it is the joint interface, there the change in area is not that much abrupt, so it will not fail from there. So correct answer will be the toe weld. So I've explained this solution, but still, if you are facing any difficulty to understand, please let me know. Otherwise, we will move to the next problem. Okay. It seems there is no doubt. Let's move to the next problem. Please read the question and try to uh, think of the solution, and you can give your response in the polling section. I will create the polls. I have launched the polls. Please give your response in the polling section. After that, we will discuss it together. Yes, I have got the response from both of you, and yes, both of you are correct. So still, let's discuss it for others. So increase in heat input in the arc welding. So what will happen after increasing the heat input? So let's quickly try the schematic of arc welding. Okay, here we have two components like this, and now we are trying to weld them. We are trying to weld them together. So what we are doing here, we are having the welding electrode. Okay, wait. Electrode, and here we are having the components which need to be joined. To be joined. Okay, so what will happen here in arc welding? We know when we bring our welding electrode near the fairing surfaces, then because of because of the power which we are supplying to, or the potential, uh, because of the potential difference between this electrode and the components need to be joined, the arc is produced, and because of that arc heating will take place. And what happens, we try to melt the material near the joint, and this melting happens because of heat produced due to the arc. And if we keep on increasing the heat input, what will happen? And when we keep on supplying the heat to this welding zone, and we know near the welding zone heat will get transferring to the other parts of the component, and because of this transfer of heat, the properties near this is the fusion zone, and the area near the fusion zone where heat transfer has took place, that is called HAZ or heat affected zone. And this heat, because of this heat affected zone, that properties of base metal gets changed. Sorry, base metal. So we are supplying the heat to the fusion zone, and that heat will get transferred to the base metal, and the region through which heat has been transferred to the base metal, that near the fusion zone, that is called the heat affected zone. So if we increase the heat, then more heat will transfer, then the heat affected zone will become larger and larger. So if we see, first option is increase in weld cross section. If we keep on supplying more heat, then this welding, more material will get melted, more material will keep on more material will get melted, so the cross section area of weld zone will increase. So that is correct. Increase in thickness of HAZ. Yes, if we keep on supplying more heat will get, the heat transfer will happen to the larger zones of the base metal, and it will affect the properties of the base metal to the larger distances, and therefore the increase in thickness of heat affected zone will happen. That is also correct. And increase in residual stress and distortion. So if you see in the heat affected zone, let's zoom out this area here. If we see our base material have microstructure something like this, but here let's say this is the melted zone, this is the melting zone, and these are the regions of the heat affected zones. So in the heat affected zones, because of transfer of heat, the microstructure will not remain same as the base metal. Some change will happen, either it will increase in size, either it will decrease in size based on the our base metal condition. So we are just taking an example where the microstructure size has been reduced like this. So because of heat transfer, heat affected zone, we have got the microstructure size has been changed, or grain size has been reduced. So because of this, if you see in near this region, earlier we had bigger size of grains, now just near the bigger size of grain we are having a smaller grain size, and this region is heated and then it gets cooled quickly. So in this region, if we see, this is the area of where the here in this region we will see the microstructures, they are not stable or they are not strain free. Basically here we have smaller structures, and here earlier we has larger grain structures, and because of this heat affected zone, there is a strain incompatibility will happen near this region. And since uh, there is a strain incompatibility, therefore uh, microstructures will not remain in stress free position, they will remain strained. So if they are they will remain strained, then what will happen? Then there will be presence of residual stress. So here strain incompatibility will be there. Ability, basically uh, our smaller grains will uh, try to pull the bigger grains towards itself, whereas the bigger grains they will not allow to move towards the smaller grains. Uh, that kind of uh, strain will happen. One side it will happen compressive, one side it will have happen in tensile mode. And because of this strain incompatibility, we will have residual stresses. And we know if we have residual stresses, if if it's tensile in nature, then there are chances of, then it can then crack propagation will happen very easily. So it will facilitate the crack propagation, and that will cause of the distortion. So if we have residual stress tensile in nature, then distortion tendency will be increasing. So it will have more distortion tendency. So this is also correct. So because of increase in heat input, we are getting higher melting zone, and we are getting higher heat affected zone. And because of higher heat affected zone, there is more area for the formation of residual stress, and we will have more distortion tendency. So the correct answer for this problem is this, all the above. So I have explained this problem. So still, if any doubts, if any of you have, please let me know. Otherwise we will move to the next problem. Okay, let's move to the next problem. Please read the problem and try to solve it by yourself first, then we will discuss it together. Meanwhile, I will create the polls. Yes, polls are live. If you are finding any difficulty to understand the problem, please let me know. Whether question is clear to all of you? If you are facing any difficulty, please let me know. I may help to understand to make you understand this problem. Yes, I have got a response. Okay, whoever have answered, that is correct. Okay, let's try to discuss it together for others. Okay, so what is given? Two 5 mm thick steel plates are placed 2 mm apart and they are welded by a butt joint, and welding is carried out at 20 volts and at a speed of 5 mm per second. Here also we are given the heat transfer efficiency is 80% or 0.80, and heat required to melt the steel is 10 joule per mm cube, and also the melting efficiency is given 0.625. And what we have to find out? We have to find out the welding current in amperes. So let's quickly draw the diagram of what has been asked in the question. So basically we are having two plates. Let's draw it in the 3D like this. We are having two plates and thickness of each plate is 5 mm. And they are kept apart of 2 mm, and they are being jointed to each other. So basically we have welding electrode and we are depositing some material in between these two plates in order to join them. So that is welding electrode. We are melting them, and after melting we are depositing the melted material in between these regions. And the current which we are supplying, that is not given, that we have to find out. And the voltage which we are using, it is 20 volts, and current, since it is not given, let's assume the current value is I. So because of this voltage and current, the heat will get produced, and that heat will try to melt the electrode. It is made up of steel, and that the melted material will get deposited in between these two plates, and the welding speed is given. So basically electrode is moving forward by 5 mm per second. So what we have to find out? We have to find out current I. So we are depositing material by melting it with the help of current, by the help of the welding current, and at the potential difference of voltage 20 volts. So let's try to find out how much material is getting filled per second. So let's try to find out how much material is depositing per second. Material getting deposited per second, that will equals to this area, this hashed area multiplied by the speed of the electrode. So that will be 5 mm multiplied by 2 mm, and that is multiplied by 5 mm per second. So it will come out 50 mm cube per second. So this much of material is getting deposited per second. So let's try to find out how much heat energy is required in order to melt this much of material per second. So let's try to find out amount of heat required per second in order to melt this much of material. So that will be coming out 50 mm cube per second multiplied by how much energy required to melt 1 mm cube. So it is given 10 joule. Basically, if we have 1 mm cube of material and we want to melt it, how much energy we have to keep? 10 joule. So in order to melt 50 mm cube, we have to multiply it by here. We have to multiply it by the 50 mm cube by the 10 joule per mm cube. So that will come out 500 joules per second. So this much of energy is required per second in order to melt the 50 mm cube of material, and this material is getting deposited in between these two plates per second. And how much energy how much heat energy we are supplying, that can be calculated by the energy which we are supplying is heat energy we are supplying will be equals to multiplication of V into I, or 20 volts into I. I we don't know, that we have to find out. So I am keeping I as it is. So energy which we are supplying comes out to be 20 I. Now what else we are given? We are given the heat transfer efficiency. So ideally we are providing this much of energy, but this whole energy will not reach to the workpiece. So some losses will be there, and that is given by the heat transfer efficiency. So we have to, how much heat is reaching to the workpiece by conduction, that we can find out by multiplying it by efficiency, or by this is the heat transfer efficiency. C efficiency. And even after this much, after the energy what is getting transferred to the workpiece, the whole energy will not get utilized for the melting. So therefore we are given a melting efficiency. The melting efficiency is given 0.625. So out of this whole energy, the energy utilize for melting purpose will be equals to 20 into I into heat transfer efficiency into 0.625, that is the melting efficiency. So we have provided energy 20 into I, and the amount of out of this energy, if we multiply it by the eta or heat efficiency, which is 0.8, and this much of heat will reach to the workpiece, and out of this heat, if we multiplied it by the melting efficiency, that much of heat will get utilized for melting the material. So total energy utilized for the melting is this much, 20 into I into 0.8 into 0.625. Now this energy should be the equals to the amount of heat required here. This energy should be equals to the amount of heat required to melt the material per second. Then only the material required amount of material will gets melted and deposited in between two plates. So what we will do, we will equate these two values. So what we will do, let's add another slide. So new slide here. Okay, okay, so now we are equating amount of energy required per second, amount of energy required per second for melting with the amount of energy supplied or amount of energy reaching to the workpiece for melting, so that will be equals to 500 joules per second should be equals to 20 into I into 0.8 into 0.625. So if we calculate the I from this equation, we will get I is equal to 50 amperes. So the correct answer for this problem will be the 50 amperes. So it is here. So I have explained the solution of this problem. If there is any doubt, please ask me. Otherwise, we shall move to the next question. Okay. Okay. Since it seems there is no doubt, let's quickly move to the next question. Later, still, if you find any difficulty to understand, please let me know. Meanwhile, I will move to the next problem. Please read the question and try to find out the correct option for this. Meanwhile, I will create the polls. Yes, polls are live. You can keep your response in the polling section. After that, we will discuss it together. Okay, I have got response from both of you. One of you got the correct answer. So let's discuss it together. So there are two statements. The first one is the partially melted grains act as a nucleant in case of same composition of base and filler material. And statement 2 is in epitaxial solidification there is only grain growth occurs but no nucleation. So let's try to see what happens during the welding when we melt the material and again material gets solidified. So here we have base material like this, and we are supplying heat. We are supplying heat near the joint. So that is the let's say arc or flame or any heating source. And when this heat when we are supplying the heat to the joint near the joint area, so what happens? uh, we here we have electrode, which is also sometime act as a filler material. So like this here. So we have these base metals and we have electrode, and because of heat the electrode is getting melted, and that is getting deposited the in between regions of the base metals. And when heat since here we are supplying the heat, so some heat is getting transferred to the base metals also. So I will zoom out this area. So what will be happening near? So here we have base materials, and because of heat what is happening, the uh, close regions in the close regions of this heating region, the base metal base metal material grains, these are these grains get uh, partially melted basically. The less because of transfer of heat, some amount of material near the flame or the heating source, they are material getting partially melted. Here we are having partially melted grains. Melted grains. And if we try to look in little bit bigger, so it is like this. Here these are the reasons where the grains are melting partially. These are the base metal, and we are supplying, we are um, we are adding molten material from the electrode, so that is getting filled in this whole region. That is the molten material. So because of it, the these are the some of the grains of the base metal get partially melted, and suppose the base, this electrode material which we have filled, they are also having the same composition, then what will happen? Then the material will get melted and it will get deposited, it will get filled between these two base metals, and after that what will happen? Cooling will take place. When cooling will start happening, then the atoms from the molten material, they will try to solidify. So there are two methods of the solidification. Suppose if the composition of filler material is not same as the base material, then what would have taken place? Then then during the cooling, there are the some regions, the, the there is a nucleation of grains. So as temperature keeps on falling, so throughout the whirlpool there is the nucleation of grains, and these grains will start growing bigger and bigger, bigger and bigger. So this process would have taken place if filler material is not of the same material. But here, since the filler material is same as the base metal, so what will happen here? The atoms from the melted material will starts getting deposited near the partially melted grains. So like here, so they don't need to get nucleated, and grain growth process will not take place. So grain nucleation and grain growth will not happen. But what will happen, since already we are having the partially melted grains, so the atoms will directly go and sit on those partially melted grains, and that grain will starts growing bigger and bigger towards the molten metal side. So it will keep on increasing, so until the whole molten region gets solidified. So this kind of solidification is called the epitaxial solidification, where already we have nucleating sites in the form of partially melted grains, and that grains keep on growing throughout the molten metal. So there is no separate nucleation and growth process will happen. The only existing grains will keep on growing towards the molten metal. That is called the epitaxial growth. Now let's look at the statements. Partially melted grains act as a nucleant in the case of same composition of the base filler material. Yes, if the filler material will have the similar composition of the base material, there is no separate nucleation of grains will happen, but partially melted grains will act as a nucleant. So yes, this is correct. Let's come to the statement 2. In epitaxial solidification, there is only grain growth occurs but no nucleation. Yes, this is also correct, because the partially melted grains, they themselves acts as a nucleant, so there is no need of separate nucleation of grains. So atoms will keep on depositing on these existing grains, and they will start solidifying, and only growth will take place towards the molten region. Yes, this is also correct. So the correct option for this is 1. Both statements are true. So I have explained this problem, but still if any doubt is there, please let me know. Otherwise we will move to the last question of the day. Okay, it seems there is no doubt. So let's move to the last question of today's session. Please read the question and try to find out the correct answer. After that we will discuss it together. You can give your response in the polling section. Yes, polls are live. You can give your response in the polling section. Okay, I have got response from both of you and both of you are correct. Let's quickly discuss it together. So advantage of high density over the lower energy density process. So here we are talking about the welding. So in welding we know we are having the heating source, and from the heating source we are trying to melt the material, and we are trying to join the both materials by locally melting it, by melting them locally and fusing them together. So there is term called energy density. So that is defined by energy density. That is the energy per unit area. Sometimes units is given in the joules per centimeter square. So we know we always try to have a source where we should get high energy density. So there are several advantages of high energy density. So suppose we are having the material which needs to be joined together like here, and we are having the energy source. So it may be flame, arc, laser, electron beam, anything. If we have a lower energy density, then what will happen? What we are trying to melt the material near the joint region, and uh, we are fusing the material, and we are joining them by fusing them. So our aim is to melt the material. So if energy density will not be higher, then what will happen? If energy density will not be higher, then we have to supply the heat for larger area. So here we are taking two cases, suppose like here we are taking low energy density, here we are taking high energy density. Our aim is to melt the material. If we have low energy density, then we have to apply energy over the larger area, and for longer periods of time. And if we keep on supplying energy till the whole material is gets melted. So suppose we are supplying the energy for 5 seconds in the both cases. Here in the case of low density, what will happen? The material which will get melted will be of lesser depth. So okay, let's do by this. Suppose we are providing energy for 5 seconds. So let's say first second energy will get this much of material gets melted. Next second this much of material which gets melted. Likewise this. So after 5 seconds this much of material will get melted. Since for given area we have low energy, so we have to provide energy for the longer time in order to melt the material. And what will happen? Since the energy will keeps on transferring here, everywhere, so larger heat affected zone will be present in the case of low energy density. Whereas if we have high energy density, then what will happen? In very smaller area we are providing higher energy. So what will happen? Since lot of energy is concentrating at very small unit of very small area, so here also we will keep on applying supply energy for the 5 second, let's say, for example. So in the first second higher energy was there, we are getting more depth of melting. Again in the next second what will happen? More material will be melted. Similarly after 5 seconds the depth of material which is melted is higher in the case of the high energy density, and that is our aim. We are not interested to melt the whole material surrounding regions. We are just interested to melt the material near the joint region. And here just by applying energy for the less time we are getting higher depth of penetration, whereas in low energy density the depth of penetration was less, but here we are getting the vast area of the heat affected zone, which was not desirable at all. So the correct answer for this is increased penetration. So if energy density will be high, the penetration will be higher. So yes, as all of you have already given the correct answer, so I have explained the reason. So if any of you have doubt, please let me know. Otherwise we will stop here. Okay, it seems it's clear to everyone. So we will stop this session here, and we will meet in the next week with a similar kind of problems based on the lectures of week 11. So I wish you all a very happy weekend. Please go and enjoy, and we will meet in the next session. Okay, thank you so much. Okay, we are ending session now. Bye, good night.